the fortress trembled. Deep beneath 4 meters of reinforced concrete, Belgian soldiers felt the impossible, a shock wave from above that shouldn't have existed. The date was 1942, and somewhere in the Belgian countryside, German engineers watched with cold satisfaction as their creation, a needle of chrome vanadium steel, punched through what military doctrine had sworn was impenetrable. The Röchling shell, Germany's most closely guarded artillery secret, had just turned the rules of modern warfare into dust. This was no ordinary ammunition. This was a weapon so classified that the Wehrmacht limited its use not for lack of effectiveness, but for fear that a single dud might fall into Allied hands and expose its terrifying potential. If you want to discover how this secret weapon worked and why it changed everything, stay with me, subscribe to this channel, and tell me in the comments where you're watching from. Let's travel back to the origins of this remarkable story. In the years leading up to World War II, Europe witnessed an unprecedented arms race, but not in tanks or aircraft alone. Nations poured billions into concrete. France built the Maginot Line, a seemingly impregnable barrier of steel and reinforced cement that stretched along its German border. Belgium constructed a network of massive forts, including the legendary Fort Eben Emael, considered by many to be the most formidable defensive structure ever built. These fortresses featured walls and ceilings of reinforced concrete measuring anywhere from 1 meter to over 3 meters thick. The conventional wisdom was simple. No artillery shell in existence could breach such defenses by direct impact. The concrete would simply absorb the blow. But the German military establishment refused to accept this limitation. Their experiences from World War I still haunted them, memories of futile assaults against fortified positions, of entire divisions ground into nothing against Belgian and French strongholds. When Adolf Hitler rose to power and began planning his conquest of Europe, he made it abundantly clear to his generals that no fortress would stand in his way. German engineering would find an answer. Enter August Coenders, an engineer working for the Röchling Steel Company in Völklingen. Coenders understood something that most of his contemporaries overlooked, the fundamental physics of penetration. When a conventional artillery shell struck concrete, it transferred its kinetic energy across a relatively wide surface area. The concrete, designed specifically to distribute and absorb such impacts, would crack and crumble, but only superficially. The shell itself would often shatter or deflect. The fortress behind would remain intact, its occupants shaken but alive. Coender's revolutionary insight centered on a principle called sectional density. Imagine 2 objects of equal mass, one shaped like a dinner plate, the other like a sewing needle. If you throw both at a block of ice with equal force, the needle punches through, while the plate merely shatters against the surface. The difference lies in how concentrated the impact force becomes. By condensing mass into a smaller striking area, penetration increases dramatically. Coenders decided to build an artillery shell that resembled, quite literally, a gigantic steel arrow. The design that emerged from his workshops defied conventional munitions doctrine. Traditional shells were relatively short and fat, maximizing explosive capacity while maintaining structural integrity. Coender's creation stretched nearly 2 meters in length, but measured barely 21 centimeters in diameter. Made from specially hardened chrome vanadium steel, it featured a wickedly pointed nose cone designed to concentrate every joule of impact energy into a tiny contact point. The rear section incorporated stubby fins for stabilization, though these worked quite differently from later fin-stabilized projectiles. A unique discarding flange served as the driving band, engaging the rifling grooves inside the barrel before falling away in flight. The prototype shells underwent their first trials in 1942 against Fort de Batisse in Belgium. This fortress, which had gallantly resisted German attack during the May 1940 invasion, now sat silent and empty, a perfect target for the new wonder weapon. German artillery crews positioned their 21-centimeter Mörser, 18 howitzers several kilometers away and prepared to make history. The first shell arced through the sky, its distinctive whistle unlike anything the observers had heard before. When it struck the fortress roof, there was no dramatic explosion, no plume of fire and smoke. Instead, the shell simply vanished. Engineers rushed forward to assess the damage. What they found made them gasp. The Röchling shell had punched clean through the concrete ceiling, traversing more than 4 meters of solid reinforcement before embedding itself in the floor below. Where it entered, the hole was barely wider than the shell itself, a neat circular puncture, rather than the ragged crater left by conventional munitions. The implications were staggering. At a single stroke, German engineering had rendered obsolete every fortress, every bunker, every defensive emplacement that relied on concrete protection. The shell didn't so much destroy the fortifications as it simply ignored them, passing through like a hot knife through butter. Reports quickly traveled up the chain of command to Hitler himself, who received the news with undisguised enthusiasm. Further testing followed at Fort d'Aubin-Neufchâteau, another Belgian stronghold that had resisted German forces during the 1940 campaign. Here, the Germans conducted more systematic trials, firing multiple Röchling shells to document their precise penetration characteristics under various conditions. The results consistently exceeded expectations. Shells penetrated between 4 and 4.5 meters of reinforced concrete before coming to rest, with some specimens boring even deeper into the earth beneath the fortress floor. The technical data emerged in careful German documentation. When fired from a standard 21-centimeter howitzer at ranges up to 1,000 meters, the Röchling shell achieved penetration figures that seemed almost impossible. 4 meters, 4.5 meters, in some tests, even approaching 5 meters of solid reinforced concrete, materials that had been explicitly engineered to resist bombardment. No defensive structure in Europe could claim immunity from such punishment, but the Röchling shell harbored a critical flaw, one that would ultimately limit its combat effectiveness and ensure it remained a curiosity rather than a war-winning weapon: accuracy. The unusual length and slender profile that gave the shell its remarkable penetration also made it aerodynamically unstable over longer ranges. Dispersion figures showed the shell could land up to 36 meters away from its aiming point at just 1,000 meters distance. At longer ranges, accuracy deteriorated further, making precise targeting essentially impossible. This presented German commanders with a dilemma. The shell could devastate any fortification it struck, but actually hitting a specific bunker or pillbox required either extraordinary luck or an impractical volume of fire. Against large fortress complexes like those in Belgium, the inaccuracy mattered less because any hit anywhere on the structure would cause significant damage. But against the smaller field fortifications that dominated tactical warfare, the Röchling shell offered no advantages over conventional munitions. There was also the matter of cost. Each shell represented a significant investment in specialized steel, precision machining, and careful quality control. Standard high-explosive rounds cost a fraction as much and could be produced in quantities sufficient to compensate for their individual limitations. German industry, already straining to meet the Wehrmacht's insatiable demands for ammunition of all types, could not justify mass production of such an expensive specialty round. Perhaps most significantly, German intelligence expressed serious concerns about operational security. The Röchling shell represented a genuine technological breakthrough, one the Allies would certainly attempt to replicate if they recovered an intact specimen. Every shell fired carried the risk that it might fail to detonate, providing enemy analysts with a complete example of German metallurgical and ballistic innovation. Given the shell's poor accuracy, the chances of duds falling into accessible areas seemed uncomfortably high. These factors combined to ensure that the Röchling shell saw extremely limited combat use. Of approximately 6,000 shells manufactured during the war, only around 200 were ever fired in actual operations. The remaining stockpiles were either destroyed during the German retreat or captured by Allied forces after the war's end. Those captured specimens provided Western intelligence with valuable insights into German engineering capabilities, confirming that the shells could indeed penetrate the remarkable depths their designers claimed. Today, visitors to Fort Hurka in the Czech Republic can still see remnants of Röchling shells embedded in the fortress walls, silent testimonies to the weapons that once threatened to revolutionize siege warfare. Museum displays throughout Belgium and Germany preserve examples of these remarkable projectiles, their slender profiles and pointed noses still conveying something of the menace they represented to Allied planners during the war years. But the Germans were not the only nation pursuing concrete defeating munitions. While Condors perfected his aeroshells, British engineers tackled the same problem from an entirely different direction. Their solution would prove even more spectacular, though it emerged from unexpected inspiration, a Walt Disney animated film. If you're enjoying this deep dive into secret weapons history, this is a great moment to subscribe and turn on notifications. More incredible stories like this one are coming soon. The problem confronting British planners was, in some ways, even more acute than that facing the Germans. After the fall of France in 1940, Germany's U-boat fleet posed an existential threat to Britain's survival. These submarines operated from massive concrete pens along the French Atlantic coast, structures built with roofs up to 5 meters thick, specifically to resist aerial bombardment. Every conventional bomb in the Allied arsenal simply bounced off these behemoths, leaving the submarines within unscathed. Unless Britain could neutralize the U-boat threat, the island nation would slowly starve. Barnes Wallis, the brilliant aeronautical engineer who would later achieve fame for his bouncing bombs used against German dams, proposed an audacious solution. Rather than trying to punch through the concrete directly, he suggested building a bomb so massive and so fast that it would bury itself deep in the earth beside the target before detonating. The resulting underground explosion would create a localized earthquake, shaking the structure's foundations until it collapsed into its own crater. He called it an earthquake bomb. The concept required a weapon of unprecedented size and sophistication. Wallis initially envisioned a 10-ton behemoth, but no aircraft in existence could carry such a monster. Compromises were necessary. The result was the Tallboy, a 12,000-pound bomb measuring over 6 meters in length and filled with nearly 3 tons of Torpex, an explosive compound 50% more powerful than standard TNT. The Tallboy's design prioritized 2 characteristics above all else: aerodynamic efficiency and structural integrity. The bomb featured a streamlined teardrop shape that allowed it to achieve near supersonic velocities during its descent from bombing altitude. Where conventional bombs might reach perhaps 400 miles per hour before impact, the Tallboy could exceed 750 miles per hour, generating kinetic energies that pushed the boundaries of materials science. To survive these tremendous impact forces without shattering, each Tallboy was cast from a single piece of specially formulated high-tensile steel. The manufacturing process was extraordinarily demanding, with reject rates initially exceeding 50%. But when the bombs worked, they worked spectacularly. Dropped from 18,000 feet, a Tallboy would penetrate over 40 meters of soil before detonating, creating craters 24 meters deep and 30 meters wide. If it struck concrete directly, it could punch through 6 meters or more before exploding. The first combat use of Tallboys came on June 8, 1944, just 2 days after the D-Day landings at Normandy. No. 617 Squadron, the famous Dambusters, attacked a railway tunnel at Saumur, France, through which German reinforcements were flowing toward the beachheads. A single tallboy struck the hillside above the tunnel, burrowed through 60 feet of rock and soil, and detonated directly above the underground passage. The resulting explosion collapsed a massive section of the tunnel, blocking it for months. Throughout the summer and autumn of 1944, tallboys devastated German infrastructure across occupied Europe. The famous Tirpitz, Germany's last operational battleship, sustained multiple tallboy hits that eventually capsized her in a Norwegian fjord. V-weapon launch sites crumbled under earthquake bomb attacks. Railway viaducts that had defied conventional bombing for years collapsed after single tallboy strikes undermined their foundations. But Wallace was already thinking bigger. Even the tallboys sometimes failed to deliver the decisive knockout blow against the most heavily protected targets. The submarine pens remained largely intact despite repeated attacks. Something more powerful was needed. That something was the Grand Slam. Weighing 22,000 pounds, nearly 10 tons, the Grand Slam was the largest conventional bomb deployed during World War II. Its explosive charge alone weighed 4.5 tons. Dropped from specially modified Lancaster bombers that had their armor, defensive guns, and most of their bomb bay doors removed to accommodate the monster weapon, Grand Slams achieved impact velocities exceeding 800 miles per hour. The effects were devastating. A Grand Slam could penetrate over 40 meters of earth or up to 6 meters of reinforced concrete before detonating. Against the Bielefeld Viaduct, a critical German supply route that had survived no fewer than 54 conventional bombing raids, a single Grand Slam brought down a 100-meter section of the structure. At the Arnsberg Viaduct, 2 Grand Slams destroyed spans that German engineers had repeatedly repaired after conventional attacks. Against the submarine pens, Grand Slams finally demonstrated their full potential. At the Valentin facility near Bremen, a massive construction project intended to mass-produce Germany's most advanced Type 21 U-boats, Grand Slams punched completely through the 4.5-meter concrete roof, bringing down enormous sections of the ceiling and rendering the facility unusable. 1,000 tons of concrete collapsed in a single strike, crushing everything beneath. Yet even these spectacular weapons had limitations. Accuracy remained problematic, particularly at the extreme altitudes required for maximum impact velocity. Weather conditions over northern Europe often precluded high-altitude attacks, and the modified Lancasters capable of carrying Grand Slams were in desperately short supply, limiting operations to small-scale precision strikes rather than systematic campaigns. This is where the Disney bomb enters our story. Named not for its creator, but for its inspiration, this remarkable weapon represented a fundamentally different approach to the concrete penetration problem. Where Wallace relied on mass and altitude to generate impact energy, the Disney used rocket motors to accelerate its descent beyond anything achievable through freefall alone. The concept emerged in 1943 when several Royal Navy officers watched a screening of Victory Through Air Power, an animated propaganda film produced by Walt Disney Studios that depicted futuristic bombing techniques against enemy fortifications. One sequence showed a rocket-assisted bomb streaking earthward at tremendous speed, punching through massive concrete structures that conventional weapons could barely scratch. The officers wondered whether such a device might actually be possible. Captain Edward Tyrrell of the Royal Naval Volunteer Reserve took up the challenge. Before the war, Tyrrell had been a lawyer and part-time inventor, holding patents for items as mundane as vegetable-peeling knives. But he possessed the crucial combination of imagination and technical understanding needed to transform science fiction into military reality. Tyrrell's design called for a 4,500-pound bomb featuring 19 solid-fuel rocket motors clustered around its midsection. Upon release from the aircraft at 20,000 feet, the bomb would free fall for approximately 30 seconds until reaching about 5,000 feet altitude. At that point, barometric switches would ignite the rockets, which burned for 3 seconds while adding nearly 100 meters per second to the bomb's already considerable velocity. The mathematics were impressive. Free-falling conventional bombs of similar weight might reach perhaps 750 miles per hour at impact. The Disney, boosted by its rockets, achieved 990 miles per hour, approximately Mach 1.29, over 30% faster than the speed of sound at sea level. This translated to an impact velocity of nearly 1,450 feet per second, generating kinetic energies that dwarfed anything previously attempted. At such speeds, the bomb required exceptional structural integrity. The warhead section featured extraordinarily thick armor steel walls surrounding a relatively modest 500-pound explosive charge. The designers accepted that most of the bomb's destructive potential would come from kinetic penetration rather than explosive force. Post-war testing confirmed the Disney could penetrate nearly 5 meters of solid concrete before coming to rest, marginally exceeding even the massive Grand Slam's concrete penetration performance. Production and testing proceeded rapidly through late 1944. Initial trials at a bombing range near Southampton established the trajectory characteristics of rocket-accelerated descent, allowing bombardiers to calibrate their sights for the unusual flight path. Then came live testing against actual German fortifications. The target selected was the Watten Bunker, German codename Kraftwerk Nordwest, a massive concrete structure in northern France that had originally been intended as a launching site for V-2 rockets against England. Captured by Allied forces in September 1944, it now served as a perfect test bed for the new weapon. 4 Disney bombs were dropped, 2 scoring direct hits that penetrated deeply into the structure. British observers on the ground reported satisfactory damage. Combat operations began on February 10, 1945, against the E-boat pens at IJmuiden in the Netherlands. These torpedo boat shelters protected the fast German vessels that regularly attacked Allied shipping in the English Channel. Despite multiple previous attacks with tallboys, the pens remained operational. 9 Boeing B-17 Flying Fortresses of the 92nd Bombardment Group carried 18 Disney bombs to the target. Each B-17 carried 2 Disneys, one slung beneath each wing on external hardpoints because the slender 5-meter-long weapons could not fit inside the aircraft's bomb bay. Cameras fitted to the bombers recorded the bomb's descent and impact. Royal Navy intelligence later confirmed that multiple shells had penetrated the concrete roof, though the pens were empty at the moment of attack. The most significant Disney operation came on March 30, 1945, against the Valentine submarine pens. This enormous facility, where 10,000 concentration camp prisoners had labored under horrific conditions, was nearing completion when Allied intelligence identified it as a priority target. 36 aircraft, including 12 from the 92nd Bomb Group, launched more than 60 Disney bombs against Valentine. 3 days earlier, RAF Lancasters had struck the facility with Grand Slams, blasting 2 enormous holes through the 4.5-meter roof. The Disney attack aimed to widen the damage and destroy equipment inside. Only 1 Disney scored a direct hit, testament to the persistent accuracy problems that plagued all precision bombing operations. But installations surrounding the bunker suffered extensive damage, and German authorities abandoned reconstruction efforts shortly afterward. Now I want to pause here and invite you to leave a comment below. Which of these incredible weapons surprised you the most? The German aeroshells or the Allied rocket bombs? Your engagement helps this channel grow, so please take a moment to share your thoughts. As we reach the closing chapter of our exploration, let's examine how these remarkable munitions fit into the broader history of concrete fortification and its defeat. The contest between bunker and bomb represents one of warfare's oldest dynamics, the perpetual struggle between defensive and offensive technologies. Throughout history, each new fortification technique has eventually encountered a countermeasure capable of defeating it. The ancient world witnessed the evolution from simple wooden palisades to stone walls to elaborate systems of towers and curtain walls. Medieval castles, seemingly impregnable in their day, crumbled before gunpowder artillery in the 15th and 16th centuries. Star forts designed to resist cannon fire eventually succumbed to high explosive shells in the 19th century. And the reinforced concrete bunkers of World War II, considered the ultimate expression of passive defense, met their match in weapons like the Röchling shell, the Tallboy, the Grand Slam, and the Disney bomb. What lessons emerged from this extraordinary chapter in military technology? Several themes deserve attention. First, the importance of physics over brute force. August Coender's genius lay not in creating a bigger explosion, but in understanding how to focus impact energy. His aeroshells penetrated concrete not by overpowering it, but by concentrating force into a tiny contact point, essentially cheating the physics that protected conventional bunkers. Similarly, Barnes-Wallis's earthquake bombs worked not by matching the bunker's mass, but by undermining its foundations, turning the structure's own weight into the agent of its destruction. Second, the crucial role of material science. None of these weapons could have existed without advances in metallurgy that permitted construction of projectiles capable of surviving tremendous impact forces. The chrome vanadium steel of the Röchling shells, the single-piece, high-tensile castings of the Tallboys, the armored penetration casings of the Disney bombs, all represented cutting-edge industrial capability that only the most advanced nations could achieve. Third, the persistent tension between capability and practicality. The Röchling shell could penetrate any fortification on Earth, but its poor accuracy and high cost limited it to virtual irrelevance. The Grand Slam was devastatingly effective, but so few aircraft could carry it that operations remained perpetually constrained. The Disney achieved remarkable penetration, but arrived too late in the war to influence the outcome. In each case, theoretical capability outran practical employment. Fourth, and perhaps most importantly, the human element that made these weapons meaningful. The Belgian soldiers who died at Fort Eben-Emael and Fort Aubin-Neufchâteau, the concentration camp prisoners who perished building the Valentin-Pens, the aircrew who flew impossibly slow and vulnerable aircraft to deliver earthquake bombs, the engineers who risked their careers championing unorthodox designs. These stories remind us that technology alone never determines military outcomes. It is always people, their courage, their ingenuity, their suffering, that give weapons their historical significance. The post-war period saw extensive testing of all the concrete-piercing munitions developed during the conflict. Project Ruby, conducted in 1946, subjected the German bunker at Heligoland and the Valentin-Pens to systematic bombing with Tallboys, Grand Slams, Disneys, and American equivalents. The results confirmed what wartime operations had suggested, that none of the existing weapons offered a perfect solution. Each had advantages and limitations. The conclusion recommended development of entirely new designs incorporating the best features of all. This recommendation bore fruit during the Cold War, when both superpowers invested heavily in fortification-defeating munitions. Modern bunker busters like the American Massive Ordnance Penetrator trace their lineage directly back to Barnes-Wallis's earthquake bombs. Rocket-assisted penetration technology, first demonstrated by the Disney bomb, evolved into weapons like the French Durandal, designed to crater runways with rocket-accelerated descent. The physics pioneered by August Coenders with his aeroshells informs modern kinetic energy penetrators that defeat tank armor through high-velocity, dense metal rods. In January 2009, visitors to the Watton Bunker Museum watched as French bomb disposal teams extracted an intact Disney bomb from the structure's roof. The weapon had embedded itself during 1945 test drops and remained there for 64 years, its 500-pound explosive charge still theoretically capable of detonation. The careful removal operation reminded observers that the legacy of these weapons remains physically present across Europe, buried in fortress walls and embedded in bunker foundations, silent monuments to one of history's most remarkable technological competitions. Today, visitors to Fort Hurka in the Czech Republic can see small-scale Röchling prototypes displayed in the Museum of Czechoslovak Fortifications. At Fort d'Aubin-Neufchâteau in Belgium, tourists walk through galleries scarred by German testing, the walls still bearing witness to the shell that shredded concrete like paper. These sites preserve not just artifacts, but memories, reminders of the extraordinary lengths nations went to in their pursuit of military advantage. The Röchling shell represented one of World War II's most fascinating might-have-been weapons. Had German industry produced it in larger quantities, had engineers solved its accuracy problems, had circumstances permitted more extensive combat employment, the defensive strategies of multiple nations might have required fundamental revision. As it actually happened, the shell remained a curiosity, a weapon of tremendous potential that never quite fulfilled its promise. The Disney bomb suffered a similar fate, arriving in combat only months before Germany's surrender. Its revolutionary capabilities never fully demonstrated under operational conditions. Both weapons remind us that technological innovation during wartime often produces solutions to problems that have already passed, answers to questions nobody is asking anymore. And yet their legacy endures. Every modern military recognizes that no amount of concrete provides absolute protection against a sufficiently determined adversary with sufficiently advanced weapons. The bunker-busting shells and bombs of World War II taught that lesson with unmistakable clarity. The fortifications that commanders once considered impregnable proved to be merely difficult, obstacles to be overcome, rather than barriers that could not be breached. This understanding shapes military construction to the present day. Modern command bunkers are built deeper underground, dispersed more widely, and concealed more carefully than their World War II predecessors. The lesson of the Röchling shell, that even the thickest concrete can be penetrated by the right weapon, remains relevant 8 decades after German engineers first watched their arrow projectile punch through 4 meters of Belgian reinforced concrete. In the end, the story of the secret shell that shredded concrete bunkers like paper is not merely a tale of engineering achievement. It is a meditation on human ingenuity, on the endless competition between offense and defense, and on the ways that technological innovation during wartime can produce weapons of extraordinary capability that nonetheless fail to change history's trajectory. August Kunders created a masterpiece of ballistic engineering. Barnes Wallis revolutionized the earthquake bomb concept. Edward Terrell brought rocket-assisted penetration from animation to reality. Each contributed something lasting to military science. None decisively influenced the war's outcome. Perhaps that is the most important lesson of all. Technology matters, but it is never sufficient by itself. Victory in World War II came through industrial capacity, strategic vision, alliance cooperation, and the courage of millions of individual soldiers, sailors, and airmen. The weapons they wielded, including the remarkable bunker-busting munitions we have explored today, were tools in their hands, not autonomous agents of history. The people who designed them, built them, deployed them, and sometimes died delivering them. They remain the true subjects of this story. If you've made it this far, thank you for joining me on this journey through one of military history's most remarkable technological competitions. The shells and bombs that could shred concrete like paper represented the very cutting edge of human engineering capability during the most destructive conflict in history. Their story deserves to be remembered, not because the weapons themselves were decisive, but because they illuminate the extraordinary lengths to which nations will go when survival seems to hang in the balance. Subscribe to this channel for more deep dives into the hidden history of military technology. Share this video with anyone fascinated by the engineering marvels that shaped the modern world. And remember, the next time you see a massive concrete structure and think it looks indestructible, engineers 80 years ago already knew better. They built the shells that could tear it apart.